Thank you. So if there's more questions, we have a Q&A session afterwards, and I'll give the floor to Yann, who's an author, co-author of the Nickel language, which has a lot of similarities with Q as well. Go for it.
Oops. Traditional. Okay. Thanks. So yeah, I'm Yann. I'm working at Twig in the programming languages and compiler group. And this is joint work with Daniele Palombi, who was an intern at the time at Twig. And, whoops, I don't want to see that. We are working, we have been developing the Nickel configuration language. It was born out of frustration and dissatisfaction at the time with configuration management. We also do DevOps work, for example, for industrial clients. And you know, this kind of thing with Ansible, this is the case for a lot of ad hoc configuration language when you need to learn the HCL or the dialect for this stuff. Well, I mean, it feels like you could use the same abstraction and idioms in all of the languages. And also, a lot of them, including HCL, if you look at the very first version, seems to start from something that is more or less YAML and then have more and more hidden, sometimes not so hidden, programming features in it. So in a perfect world, I think configuration should be JSON, but this is not the case today. I think to handle like Kubernetes deployment, cloud deployment in general, build systems like in Nix, there is too much complexity right now, and so if you have to use programming, at least do it right somehow. So we couldn't solve all the issue of configuration management. So I mean, you have a lot of things to do, but at least as a language people, we think like we could act on the language part at least of this, and the developer experience. We talked about LSP before. I think is a huge thing. So this is the motto that I wrote someday totally randomly on the websites. But yeah, the idea is that Nickel is to bring in abstractions and nice things to handle complex configurations. And the data model is basically JSON plus functions, like in order to derive data from other data, to do a bit of data processing. And in Nix, it's really, really annoying not to have typing. I mean, users complain about that all the time because you never know what your function is accepting. You have to read the doc and often the code, actually. So we wanted typing, at least for those like functions, computations. But for configuration, as we also discussed before, I think validation makes much more sense because it's mostly static data. So typing doesn't buy you much. Typing is about flow of property across function and computations. But there you can just do validation and call it a day, and it's much more powerful because write a static type for a port number is really hard. Write a validator for a port number is a 3-line programs. So we have this kind of built-in contracts you can think of as runtime types. So you write them as type. You can spin off your own, use array and dictionary constructors, and use annotation as well. But they are checked at runtime. And it's useful in Nickel because we wanted to have schema definitions in the same language. And then, taking inspiration from Q and the NixOS module system, we have a merging operator that is as well some kind of algebraic operation that allow you to combine recalls together, which is exactly the idea of matching those trees or graph actually, because you can have self-references together. So it's a form of unification, although Nickel is still incomplete, so it's not implemented as unification, but the specification probably could be so it's somehow like if Nix, Q, and type bracket had a baby, but that's not how we thought about it, right? That was not the idea. We just had some kind of design goal, and it ended up that way. A quick primer, so this is just to show an example. It won't be very important for the rest of the call, but I couldn't resist. So this is just a function definition, something that derive a port from a protocol. Protocol is given as an enum, a bit like C enum or TypeScript enum. And we use a type annotations. We have a fancy type system with row polymorphism, and I mean a structural type system that makes sense for JSON. And we don't specify the return type. We say, please infer it. But the point is that this small part really looks like some kind of OCaml, like it's a statically typed ML language. Nickel will insert contract to protect this function if you call it from dynamically typed code. And code is dynamically typed by default. So you have to put types where you want the static type checker to kick in. And then, a bit like in Q, you don't have a strong separation between schema, values, and a bit more, but still, schema are just normal records with missing values. And we use this pipe operation to attach metadata, including contracts, to some fields. And those will propagate through merging. So I can never override extra.port with something that is not a port number. And port number is a custom contract. I didn't include it, but it's like a 5-line function that user can define. The other is a built-in enum types, and you can put a default value for protocols that depends on extra.port. That says that if you don't specify the protocol, I will try to compute it from extra.port. So as in Q, once again, records are recursive, so to speak. You can have data dependencies within your thing. And then servers using all the other yet to be defined values to produce something. And you merge that with the concrete values, which is more or less your actual high-level definition or configuration. And if you try to export that, you get what you expect in JSON. So for configuration language, a strong question that could be asked is, do we care about performance? And that's a question that we wonder at the beginning because, it's a very specific language. It's a scriptic language. You don't run it as a server in an infinite loop. You run it once during deployment. Maybe your deployment is very long anyway. So we didn't want to care too much about performance at the beginning. Just tried not to implement features that would be obviously hurting performance, like breaking parallelism, for example. Let's try to keep it pure. But still, otherwise, optimizing along the way, but we didn't think too hard and say, okay, let's wait for people to complain and see actual cases that we can, investigate and see what we can do. And it turns out that, GCL people showed at their scale, but even without going Google scale, we do care about performance. So Nix packages, the repository with all the Nix package definition, takes 8 minutes to evaluate on CI. That's actually pretty fast. I'm suspecting they use a beefy machine because Nix is not very fast and the code base is huge. But it's still 8 minutes on each pull request, After I submitted this talk, and 1 month ago, someone came to me and said, hey, I have this code base in Nickel. It's like 24 KLOC plus 15 of JSON, so it's really not huge. And it's taking 80 seconds to run. So it's a bit unacceptable. So we could bring it back to 3 seconds, but it's still a bit much. But so even on mid-sized code base, a DAL issue from a few years ago, but I honestly don't think this has been fixed because it's quite fundamental. Same kind of order of magnitude, less YAML to KLOC, 30 seconds to evaluate. So, performance is an issue in practice. And I haven't mentioned, but I think JSONet also had issues. And so what can we do about it? Well, if you have a slow program, the first thing you could say that, well, optimize the program, right? Maybe you're doing stupid stuff, you're having quadratic behavior, but you can only go so far. If your interpreter is dog slow, your program will be dog slow at some point. So what you can do is to optimize the interpreter. Do not change things like fundamentally, but have better data structures, implement some optimizations. And, it can get you quite far. But at some point, if your interpreter is, for example, a tree-walking interpreter, you will hit some hard limits. And the general wisdom with scripting language is to go for bytecode compilation. And once you have a bytecode compiler, you can, apply optimization on the compiled version and up all the way to JIT. The thing is, from step 3, this starts to be a lot of work. You have to design the intermediate representations. You have to write a compiler, which is quite different from an interpreter. You have to write a virtual machine that operates on the bytecode. And especially point 4 is not obvious to me at all because, once again, this is why we have a specific workshop. It's a very strange domain space configuration, and some optimization might not make sense. Nickel, for example, has lazy evaluation. It doesn't have any loop construct. You do that with recursive functions. But so typical optimization don't really make sense in lazy evaluation. You don't have loop invariant called loop motion because you don't have loop, but you have other things like let floating code, and also you don't do a lot of computation on numbers, or you don't expect to, so you don't care about constant propagation. So it's not obvious at first to say like what can we take from the existing wisdom such as Python, for example, to apply here. So I propose it's not totally orthogonal. I'm lying a bit, but a different avenue at least, which is based on a very simple observation, is that changes seems to be small and localized on your code bases. I mean, it's good practice at least to do so. And so then I would try, can we have something that take advantages of that so that reevaluation upon small changes is fast? And it's not, of course, you can do the computations, all these API are public, so it's not a scientific proof, but it's just a small illustration on Nix packages. It's massive. It's like 2.5 million line of code across 28,000 files. And I just took the last 5 pull requests. It's all package updates, and it's like 9 line diff, 1 file, 11 line diff, 1 file. This one is 80, 80 line diffs, 1 file, 4 line diff, 1 file, and so on. And all those have to reevaluate Nix packages completely. Which is not very efficient. And I had to scroll a bit to find the first one that wasn't just a package update. And it was the addition of a new package, and it's still like 44 lines out of 2.5 millions and 1 file. And we've mentioned that also before, in that when you work on configuration, it's a bit more akin to compilation than like running a Python script on some data, because each time you change the code, you interpret it. If it loops, you can stop it, and you get a result on fixed input and rinse, repeat. And what do compilers do? Actually, they have the exact same hypothesis, and they do incremental compilation. Sorry. So a lot of incremental X, so try to not mix them up. And yeah, so moving that to the interpreted world, it would mean that we could try to do something like incremental evaluation. And there's a more general setting out there in the literature. It's called incremental computations or self-adjusting computations, which is about efficiently recomputing a function after making a small change to its input. And as I think Marcus said, evaluation is a function from program to value, so it's trivially part of incremental computation. So that's great. We can look at the literature, and it seems to be somehow a solved problem, at least for algorithms. Usually the main application is more a specific algorithm, like you want to, aggregate a lot of data and metrics on a huge matrix, and if you change one row, for example, you want the result to be, but still, it's just an instance, so why not? And there is in particular this Adapton paper about composable domain-driven incremental computation, which is interesting because they provide some kind of language with built-in incremental evaluation, and also it's domain-driven, which really fits the lazy evaluation of Nickel. So yeah, there are differences with the other previous self-adjusting computation frameworks, is that in usual frameworks, what you do is, because you want to compute the result anyway, when you have a change, you eagerly propagate it and recompute everything. But that doesn't really fit domain-driven. So in Adapton, what you do is that you build at runtime a graph with dependencies between things. So here it's just a recursive calls to a map function defined standardly, as you can imagine in OCaml, for example. And each call depends on the previous one and on the X of the tail and so on. And when something changes, they just dirty the node and all the things that depend on it, but they don't recompute. Only when you request the node, like from the top of the graph somehow, then you start to look at, is my thing dirty? Yes, I need to recompute it or not. So it decouples dirtying from recomputation. And yeah, perfectly fits lazy evaluation, at least from a distance. But if you look a bit closer that don't really do what we want to do, because adaptant provides a language to write incremental algorithm in, and in particular, the programmer is in control of what is incremental or not. In Nickel, we would like it to be a total implementation detail. That, when you write a configuration, you don't care about this kind of complex things. You just want the thing to be fast. So, if one thing what we should do maybe is to rewrite the Nickel interpreter in adaptant, that would make sense, but not really to use adaptant as a base for semantics for Nickel. In adaptant, the incrementality came from mutations. They have an ML language with mutation, because if your language is perfectly pure and you only cache things, you have no reason to change input, nothing changed actually. While in Nickel, so there are actually some sources of incrementality, which should be the merge semantics when you override the default value, but that's not really the important part. I think what matters is the reevaluation, incrementality across reevaluation. And it's a bit different because what you change is the function itself, or the code, and not the inputs. And yeah, adaptant comes with this call by push value semantics, and it bakes the adaptant algorithm somehow, at least specification inside the semantics. And on the other hand, what I would like is something, once again, there's only one thing to remember is I want this to be non-invasive, as decoupled as possible from the interpreter, but both semantically and in the implementation. But we can adapt adaptant. And that's what we've called cache call by name for now. And if you, in particular, we would like to keep call by need is just lazy evaluation for those who maybe not into this kind of words. And call by name is a strategy where basically you recompute everything all the time from scratch. So it's totally stupid when you implement a programming language, but semantically it's actually one that has very nice properties. And when you think about lazy evaluation, you can actually see as a cache version of call by name. But it's just that it's a very, not very, but still specific version, because you cache all let bound expressions and only them. And you only cache things. So that's why there's no notion of dependency or incrementality, as I said initially. If your language is pure and you only cache things of type, of first order type, or zeroth order type rather, there's nothing that changes, so there is no recomputation to do. And so I think we can extend this to a generic notion of cache that is decoupled from the call by name evaluator on semantics. And even in call by need, when you formalize it, the formalization I know usually rely on something called explicit substitution, but the thing is that you represent the caching inside the language. And so once again, that's not something I want to do. I want the cache to be something external. So honestly, this is how I think about it right now. If I ever write a paper, I would have to do that more seriously, so don't pay too much attention. Those are draft ideas more or less. I haven't done the proof. But what's important is that I would have in my operational semantics an external notion of cache, a bit like a heap or a store when you do the operational semantics of an imperative language. But these things will be just a cache that sometimes you can ask, hey, is this value cached? Yes, give me, otherwise I just proceed to full evaluation. And it just, what the cache must do is, of course, return things that have exactly the same behavior as what you're trying to compute initially. How do we implement that? Well, in fact, call by need is already a very nice and somehow minimal interactive implementation of cache call by name. What I mean by that is we've looked into using adaptant to implement the interpreter, but the adaptant libraries that they provide, for example, in Rust and OCaml, they forces you to put things everywhere. The things that must be cached are function. So somehow you are doing you are passing continuations, and this is the usual naive way to implement an interpreter. When you say eval a plus b, well, eval a, eval b, and then I sum. Even a simple interpreter that is not a toy project is usually a stack machine, so you don't want to actually nest your function calls. But that's what code by init does. The idea is just that you have an API between the cache and the interpreter, and you just have a few back and forth, but they are rather minimal. What you do is that when you see something that should be cached, you just allocate a new node in the cache, saying, oh, I want this to be cached, and for example, you get back an identifier, pointer, whatever thunk in code by init. When you see a usage of something that should be cached, well, you try to fetch it from the cache. If it is great, you just evaluate it. I mean, you just keep it. If not, you push a marker on the stack. So in lazy evaluation implementation, it's called thunk update frame, something like that in Haskell. But you just remember that, oh, I'm evaluating something on the cache, so I will have to update the cache later on. So you go on, and when you finally pop the marker, you update the cache. So it's a very simple interface of get, set, and allocate something new with a unique identifier, so to speak. I don't think we need much more, at least from the interpreter. The cache will have to do more things for incrementality, but the interpreter should be fine. Something that is not apparent in the semantics, but because somehow it's pushed into the abstraction of the cache and is very important and probably one of the most difficult problems I think in practice, is what I call a naming scheme, but you can think of it as hashing. So when you do incremental computation, like in Adapton on one program, you don't have this problem because you think that you cache, you allocate them in the cache, and then you get a pointer or an identifier, so you can always identify them. When you want to do caching across evaluations, you have to match the things that you get after modification to the things that were there before modification. And you cannot rely on names anymore. So you need to have a way to provide an identifier or name or to identify expressions from just the expression itself. And you can do something, I mean, the dumbest one is to just identify things that are physically equal, as more or less what call by init does. If you only cache things that come from the source code and say that everything that is generated during evaluation is not cached, that's a possibility. You can just hash the source code. And then you have, a whole continuum of different trade-offs, but the general idea that you want is my naming scheme should be hashing modulo some equations. And the ideal equation that you would like, of course, is like modulo beta equivalence, that things that behave exactly the same. Of course, that's undecidable, so you cannot do that. But you can do a lot of things in between and have to find the thing that is like the right trade-off in practice between, because this has a cost as well, so it has to pay for itself. And in fact, this notion of names is also in a follow-up of the Adapton paper, but once again, they don't care about automatically doing the names. The programmer has to come with the naming scheme, so to speak. So once again, maybe something to implement the interpreter in, but not going to help us for a language with automatic evaluation. So this is very much a work in progress. Actually, since Daniele left, I haven't had a lot of time to dedicate to that, but there was a bit of refactoring to decouple the evaluation cache from the virtual machine, I mean the thunk, abstracting the thunk somehow in some interface. Is almost done incremental merging, so as a stepping stone, we first wanted to inside one evaluation using incrementality so that if you override the default value or override a value in a recursive record, you only recompute what's needed. I don't think it's very useful because in practice, what happens is that you merge a lot of stuff and then you export. I mean, I don't expect that it's a very common workflow to, compute some values and override them, compute some values, override them. Usually, you just combine everything. But still, it's interesting as a first step. And yeah, the thing that we would like eventually to do is incrementality across evaluation. And the big things is to try and to find the right naming scheme. Persistence is more of an engineering problem, like what is the format of your cache, how do you write the cache on disk efficiently and so on. But scientifically, it's not that of a huge problem. So yeah, the idea behind cache called by name is to have an abstract notion of evaluation cache. And we could even, and maybe you want to try that, to switch cache implementation depending on your workflow. Like maybe this is a program that you won't reevaluate incrementally, so you don't need the incremental cache, so I just want call by init. And that's something that's possible if your interpreter is, decoupled enough from the cache notion. You can try, and also the cache, at least in Nickel, will in fact implement part of garbage collection as well, because it will hold value, and you can try different garbage collection or cache eviction strategies. And the important point is to keep your usual call by name semantics. You don't have to rewrite the semantics of your language. And it's important because in Nickel, for example, there is something we want to implement, but it's not there yet, called custom merge function. Whatever the details, this is something that is a really natural definition in call by name, because somehow you need to see the whole merge tree to decide how to interpret it, but not so natural in call by need. So that's the point, that call by name can be usually the domain, the framework that you may want. And also, yeah, with this idea of just having an abstract cache interface, we are trying to make it easy to integrate with an existing interpreter with minimal changes. So yeah, that's it. We have a bunch of projects around a Nickel, and this is done as part of my work at Twig, and I'm happy to answer any questions.
Thank you, Yann. Maybe one or two questions before we move into the panel. Any questions? Yeah.
So thanks for the very nice talk. We have worked on incremental abstract interpretation in the past, and we were using tree differencing to determine the differences between two versions of a program that we were analyzing. So, and I didn't quite get what you were using in your talk.
So you mean to see the differences between
two successive versions of the program?
Yeah. So the idea would be to, at least for now, would be to not have any kind of diff mechanism between sources, but you just keep the cache of the last evaluation. So somehow all the values you've seen using the naming scheme and maybe some kind of strategy. You don't want to cache everything. Right now we want to start with record field, for example, and not let bindings. But so you have this set of expressions that you can identify using, for example, hash consing. That would be a probable first step. And then the second time you evaluate your thing, when you try to fetch from the cache, if you've seen the thing before with the same name or hash, then you would use that. So somehow we sidestep that and probably push it to the hashing, naming scheme. But maybe, I don't know if that's...
Yeah, anybody else? Otherwise, Ruben and Ilwa, maybe you can come to the front. Yeah.